Howdy. Welcome to the last part of the course. Up to now we've been focusing exclusively on deductive logic. We turn now to inductive logic. Inductive logic evaluates arguments and inferences that are not deductively valid. This brings a whole new set of problems, and we need to develop a new toolkit to deal with them. The central concept that we will be focusing on is the concept of probability. In this and the next two modules, I'll introduce some of the basic concepts of the probability calculus. This video is an introduction to thinking about probability. I begin by reviewing the basic differences between deductive and inductive logic, and then go on to introduce the notation that we will use in thinking about probability. Some of the notation will be very familiar to you, since we'll be studying the probability of sentences and using the Boolean connectives to construct compound sentences from more basic ones. In fact, there are some definite parallels between propositional logic and the probability calculus, which I will bring out. Once we have the notation in play, I will explain the basic framework principles that we'll be using in thinking about probabilities. Most of these will probably be familiar to you from other courses. So here are the learning objectives for this video. After watching it, you should first be familiar with the differences between deductive and inductive logic. Second, understand the notation that we'll be using to discuss probabilities. And third, be familiar with the basic framework principles governing how we'll be thinking about probabilities. So we looked at the distinction between deductive and inductive logic right at the beginning of the course. I imagine, though, that it will make more sense now, since hopefully you have a much better sense of what deductive logic is. So let's look again at the basic distinction. Here it is. Deductive logic, deductive reasoning sets out to prove conclusions from premises. The relation between premises and conclusion is logical consequence. And in contrast, we have inductive logic. Inductive reasoning includes all arguments where the relation between premises and conclusion is weaker than logical consequence, i.e. it actually is possible for the premises to be true and the conclusion false. The characterization of deductive logic should not surprise you by now, and nor should it come as a surprise that there are examples of reasoning that are not deductively valid. Deductively valid arguments are the exception, not the rule. We do not encounter them very often in everyday life, and they are almost completely absent from the sciences. So let me make this contrast a little more precise. As we've seen repeatedly, an argument is deductively valid when it's not possible for the premises to be true and the conclusion to be false. We've looked at different ways of making this notion of logical consequence more precise. In propositional logic, for example, we use the notion of tautological consequence, while in full first-order logic we talk about first-order consequence. However we develop the idea, though, logical consequence has a very important property. It is in essence pass-fail. An argument is either logically valid or it is not. There is no grey area in between. But inductive arguments are not like this. Some are better than others. We talk about the strength of an inductive argument, and strength comes in degrees. It's the job of inductive logic to set out the standards that make the good arguments good and the bad arguments bad. In doing this, the fundamental concept that inductive logic uses is the concept of probability. Roughly speaking, an argument is inductively strong if and only if it's probable that its conclusion is true when its premises are true, and conversely, an argument is inductively weak when it's probable that its conclusion is false when its premises are true. But of course, from a logician's point of view, this way of thinking about what makes arguments inductively strong or inductively weak, or somewhere in between, needs to be made much more precise. And in order to do that, we need a way of measuring probability and calculating how likely a sentence is to be true. And that's where the probability calculus comes in. The probability calculus is a relatively simple mathematical framework for measuring probability. It's made up of a set of rules that determine how to calculate the probability that a sentence is true. Some versions of the theory think of probability as a relation holding between events, so that the rules of the probability calculus are really rules for determining how likely an event is to happen. For our purposes, the distinction between sentences and events is not very important. But I'll stick with talking about sentences because that makes clearer the continuity between probability and propositional logic. This is important because there's an important parallel between the probability calculus and propositional logic. As we've seen in great detail, propositional logic tells us how to determine the truth value of a compound sentence from the truth values of the atomic sentences from which it's made up, together with the meanings of the truth functional connectives. The probability calculus does something very similar. It tells you how to determine the probability of a compound sentence given the probability of the more basic sentences from which it's built up. Moreover, just as propositional logic does not have anything to say about how to determine the truth values of atomic sentences, the probability calculus is silent on how the original probabilities are assigned. What the probability calculus tells us to do is how to combine probabilities. In fact, the resemblance is even closer, and we can see it reflected in the notation. We'll often use sentence letters in place of writing out the sentence in full, and we'll use the abbreviation P of Q to mean the probability that Q is true. Moreover, we'll use symbols for the Boolean connectives to indicate how compound sentences are built up from simpler ones. So, for example, P and Q means the probability that the sentence P and Q is true. P not Q means the probability that the sentence not Q is true. And P or Q means the probability that the sentence P or Q is true. The rules for the probability calculus basically tell us how to work out the probabilities of these and other compound sentences. So we'll start looking at those rules in the next video. But before doing that, I want to introduce 4 basic principles that set the framework for thinking about probabilities. I call these the framework principles for probability. So starting with framework principle 1. This is that probabilities are numbers in the closed interval 0, 1. You may remember from other courses that a closed interval is one that includes its endpoints. So the closed interval 0, 1 includes both 0 and 1. And in the probability calculus, the endpoints do very important work. If the probability of Q is 1, then Q is absolutely certain. It's necessarily true. And if the probability of Q is 0, then Q is impossible. It's necessarily false. So framework principle 2. This follows from framework principle 1. All tautologies have probability 1. And this makes perfect sense, since all tautologies are necessarily true. Framework principle 3 is really another consequence of framework principle 1. All contradictions have probability 0. Again, this makes perfect sense, since contradictions cannot possibly be true. And then finally, framework principle 4, if P and Q are logically equivalent, then the probability of P is the same as the probability of Q. In other words, logically equivalent sentences have the same probabilities. This makes good sense too. If 2 sentences are logically equivalent, then they're true in exactly the same circumstances. So you would expect the likelihood of their being true to be exactly the same. So, those are the 4 framework principles. In the next video, we'll start on the rules for the probability calculus. See you then.